Hello everyone, my name's Iman. Welcome back to my YouTube channel. Today we're going to finish our lecture on circuits, and we've made it to the third objective. Unlike resistors, which dissipate energy, capacitors store energy in the form of electric charge. But to understand capacitors, we first need to define capacitance. Capacitance is the measure of how much electric charge a capacitor can store at a given voltage across its plates. The relationship between charge, capacitance, and voltage is given by this equation right here that says C is equal to Q divided by V. C is capacitance, and this is measured in units of farad. This is equal to Q, which is the magnitude of charge stored on one plate, divided by V, which is the potential difference across the plates. This equation tells us that the greater the capacitance, the more charge the capacitor can hold for a given voltage. And again, the SI unit of capacitance is the farad, where 1 farad is equal to 1 coulomb per volt. Now, the simplest type of capacitor is a parallel plate capacitor, which consists of two metal plates separated by a small gap. The capacitance of a parallel plate capacitor really depends on its geometry, specifically the area of the plates and the distance between them. For a parallel plate capacitor, where two conductive plates are separated by a distance d, the capacitance can be calculated using this equation right here. This equation says that capacitance is equal to epsilon naught, which is the permeativity of free space, and this is equal to 8.85 times 10 to the negative 12 farad per meter. And that's multiplied by this term right here, A divided by D. A is the area of each plate. D is the distance between the two plates. This formula shows us that increasing the area of the plates increases the capacitance, while increasing the distance between the plates decreases it. And this makes sense intuitively because larger plates can store more charge, and placing the plates closer together is going to enhance the interaction between the charges. Now, when charge is stored on a capacitor, an electric field is established between the plates. This field is uniform, and it points from the positively charged plate to the negatively charged plate. And the magnitude of the electric field between the plates is given by this equation. This equation says that the magnitude of the electric field is equal to V, which is the potential difference between the plates, divided by D, which is the distance between the plates. And this relationship shows that a stronger electric field is created when either the voltage across the plates increases or the separation distance decreases. Because capacitors hold charge, they also store potential energy in the electric field between the plates. And the amount of energy stored in a capacitor can be determined using this equation, which says that the stored energy is equal to 1/2 CV squared, where C is the capacitance, V is the potential difference between the plates, and this equation tells us that the energy stored depends on both the capacitance and the square of the voltage. Now, let's discuss how we can enhance the performance of a capacitor using dielectric materials. A dielectric is an insulating material placed between the plates of a capacitor. Its primary function is to increase the capacitance by reducing the electric field within the capacitor. When a dielectric is introduced, the new capacitance is related to the original capacitance by this equation. And this equation says that the new capacitance is equal to the original capacitance multiplied by the dielectric constant. The dielectric constant of a material measures how well the dielectric can reduce the electric field. Dielectrics allow capacitors to store more charge for the same voltage, improving their energy storing capacity. This is why capacitors in electronics often contain materials like ceramics, which have high dielectric constants. Keeping that in mind, let's jump into two practice problems. This first problem says the voltage across the terminals of an isolated 3 microfarad capacitor is 4 volts. If a piece of ceramic having a dielectric constant equal to 2 is placed between the plates, find the new charge, the new capacitance, and the new voltage of the capacitor. So to start, let's focus on calculating the new charge. The introduction of a dielectric by itself, it has no effect on the charge stored on the isolated capacitor. There is no new charge, so the charge is the same as before, and we can write the following equation to calculate the charge. Charge is equal to CV, where C is the capacitance and V is the voltage. And we have both of these quantities, so we can go ahead and plug them into this equation. The capacitance is equal to 3 microfarad, and the voltage is equal to 4 volts. 3 times 4 is equal to 12 microcoulombs. So our charge, to start off with, and our new charge are both equal to each other, and specifically they're equal to 12 microcoulombs. Now, what about our new capacitance? Now, introducing a dielectric with a dielectric constant of 2, this means that the capacitance of the capacitor is multiplied by 2. So our new capacitance is equal to the dielectric constant multiplied by the original capacitance. This is equal to 2 multiplied by 3 microfarad, and this gives us a new capacitance of 6 microfarad. Now last, we want to calculate the new voltage of the capacitor after we've introduced this dielectric material. The new voltage can be calculated by using the charge and the capacitance. This voltage is equal to charge divided by capacitance, specifically the new charge divided by the new capacitance. This is equal to 12 microcoulombs divided by 6 microfarad. And this gives us a new voltage that's equal to 2 volts. And with that, we are able to solve the problem. We calculated the new charge to be equal to 12 microcoulombs. We calculated the new capacitance to be equal to 6 microfarad. And we calculated the new voltage of the capacitor to be equal to 2 volts. Let's go ahead and tackle the second problem. This second problem says a 3 microfarad capacitor is connected to a 4-volt battery. If a piece of ceramic having a dielectric constant equal to 2 is placed between the plates, find the new charge, the new capacitance, and the new voltage of the capacitor. Now, this question is very similar to the previous one, but the voltage here is held constant by the battery. And so that means our new voltage is equal to our initial voltage, which is equal to 4 volts. Now let's also calculate our new capacitance. This is just going to equal our original capacitance multiplied by our dielectric constant. This is equal to 3 microfarad multiplied by 2. This gives us our new capacitance that's equal to 6 microfarad. Now finally, we can calculate the new charge on the capacitor. This is going to equal our capacitance multiplied by our voltage, and specifically the new values of both that we just calculated. So this is going to equal 6 microfarad multiplied by 4 volts, and this gives us a charge of 24 microcoulombs. So for the second example problem, it was very similar, except that the new voltage is still 4 volts And then using that, we were able to calculate the new capacitance to be equal to 6 microfarad and our new charge to be equal to 24 microcoulombs. And with that, we can move into our next topic. By understanding capacitance and the role of capacitors, we now have insight into how circuits can temporarily store and release energy. Capacitors, much like resistors, can be combined in different ways within a circuit. And how capacitors are arranged affects the total capacitance and how charge and voltage distribute across them. When capacitors are connected in series, they're arranged end to end so that the same charge flows through each capacitor. However, because the voltage source must be distributed across all of the capacitors, the total capacitance decreases in a series arrangement. This means the capacitors collectively cannot store as much charge at a given voltage compared to a single capacitor. So in a series configuration, the reciprocal of the total capacitance is equal to the sum of the reciprocals of the individual capacitances. So the reciprocal of the total capacitance is equal to 1 over C1 plus 1 over C2, so on and so forth. And this equation shows that adding more capacitors in series reduces the total capacitance. Now, conceptually, this happens because the total charge on each capacitor must be the same, but the capacitors must share the voltage drop across the loop. This means that each capacitor only experiences a fraction of the total voltage. As a result, the combined capacitors behave like a single capacitor with reduced ability to store charge at the applied voltage. Series arrangements are often used in circuits that require higher voltage tolerance. Since each capacitor in the series takes on only a portion of the total voltage, the risk of overstressing individual capacitors is reduced, making it possible to handle higher voltages safely. Now, what about in a parallel configuration? The capacitors here are connected directly across the same 2 points in the circuit, meaning that each capacitor experiences the same voltage as the source. In this arrangement, the total or equivalent capacitance is the sum of the individual capacitances. So the total capacitance is equal to C1 plus C2 plus C3, so on and so forth. This equation indicates that adding more capacitors in parallel increases the total capacitance because each capacitor adds additional surface area for storing charge. Since all capacitors are exposed to the same voltage, the total charge stored in the circuit is the sum of the charge stored on each capacitor. Parallel capacitors are useful when large amounts of charge need to be stored, as the total capacitance increases with each added capacitor. This configuration is often used in applications like power supplies, where maintaining a stable voltage across components is really important, even if individual capacitors are limited in their capacity. Now that we've explored both resistors and capacitors in series and parallel arrangements, it's important to step back and compare how current, voltage, resistance, and capacitance behave in these two types of circuits. This comparison will help solidify the relationships we've discussed and show how these different components influence circuit behavior. This table you see here outlines the key differences between series and parallel circuits in terms of current, resistance, voltage, and capacitance. Here are the key takeaways, starting with current. In a series circuit, The current is the same through each component as there is only one path for it to flow. But in a parallel circuit, the total current splits among the branches with each path carrying part of the total current. What about resistance? In series, resistances add together, increasing the total resistance. This makes it harder for current to flow. In parallel, though, the reciprocal of the total resistance is the sum of the reciprocals of the individual resistances, which decrease the overall resistance and allow more current to pass through. Then we have voltage. In a series circuit, the voltage is divided across the components, with each one experiencing part of the total voltage. But in a parallel circuit, each component receives the same voltage as the source. And finally, we can talk about capacitance. For series capacitors, the total capacitance is reduced because the capacitors must share the voltage drop. And here we can write that the reciprocal of the total capacitance is equal to the reciprocals of the individual capacitances added together. So 1 over the total capacitance is equal to 1 over C1 plus 1 over C2, so on and so forth. But for parallel capacitors, the total capacitance increases as the individual capacitances add up, allowing more charge to be stored. With that, we've reached our final objective, titled meters. Although we won't dive into analyzing circuits using these devices in this lesson, understanding how meters work is crucial for real-world applications. Ammeters, voltmeters, and ohmmeters are the primary tools used to measure current, voltage, and resistance, respectively. Let's start with talking about ammeters. These measure current. So they're used to measure the current at a specific point in a circuit. Since current only flows through active circuits, the circuit must be on for the ammeter to provide a reading. To measure the current correctly, this ammeter is placed in series with the circuit element where the current is flowing. And they work by leveraging the magnetic field produced by current-carrying wires, causing a needle to deflect or a digital display to show the current reading. In circuits with high currents, an ammeter can become overwhelmed. In such cases, a shunt resistor, this is a low resistance path, is connected in parallel to protect the meter by diverting part of the current. For accurate readings, the ammeter must have negligible resistance, ideally approaching zero resistance, to avoid altering the current that it measures. And an ideal ammeter would have no voltage drop across it, and thus would not affect the circuit's behavior. Now, what about voltmeters? They measure voltage, and they're used to measure the voltage drop between 2 points in a circuit. The voltmeters also require an active circuit to function, as voltage is only meaningful when current is flowing. Voltmeters are connected in parallel across the points where the voltage is being measured. And since a voltmeter is connected in parallel, it ideally has infinite resistance. This prevents any current from flowing through the voltmeter itself, ensuring the circuit behaves as it would without the meter in place. Now, in practice, real voltmeters have very high resistance to minimize their impact on the circuit. Finally, we can talk about ohm meters. They measure resistance, and they measure the resistance of a specific circuit element. So, unlike ammeters and voltmeters, ohm meters do not require an active circuit. In fact, using an ohm meter on an active circuit can result in an inaccurate reading or even damage the meter. Most ohm meters have a built-in battery that applies a known voltage across the component being tested. and the meter measures the resulting current and uses Ohm's law to calculate the resistance. Since the goal is to measure a specific element, only one resistive component should be in the path being tested by this meter. So in summary, each type of meter plays a specific role in circuit analysis. Ammeters measure current and are inserted in series with minimal resistance. Voltmeters measure voltage, and they're connected in parallel with high resistance to avoid interfering with the circuit. And ohm meters measure resistance operating without active current, and they apply their own voltage for accurate readings. And with that, we've completed our chapter on circuits. I hope that this was helpful. In the next video, we're going to jump into a practice problem set. Other than that, good luck, happy studying, and have a beautiful, beautiful day, future doctors.